So let's think about potentials that depend on distance, and therefore the Schrodinger equation looks like or the time-independent Schrodinger equation looks like this. And let's consider a natural choice of coordinates would be spherical coordinates. So r, theta, phi, and del squared in those coordinates looks like, we won't derive this, we'll just write it down. There's an r part, right, derivatives with respect to r. There's a theta part, derivatives with respect to theta. And there's a part that has derivatives with respect to phi. Okay, so this is the operator. This is what it looks like. And for simplicity, and because we want to take advantage of the one-dimensional techniques that we're familiar with, let's start with solutions that are spherically symmetric. Okay, so they don't vary in theta and in phi, and so all of this goes away. And so del squared becomes just this, second derivative in r plus 2 over r d by dr, which of course we can combine into a term that has two derivatives in r of r times psi. Right, so this is that. Sorry, I need a psi here. So now it's the same thing, and the Schrodinger equation becomes minus h bar squared over 2m, two derivatives in this r psi, plus potential times r psi equals E times r psi. And normally the function r psi is defined as u. And so this looks like an equation for this u function. And the reason we write it in terms of this u function is that we're familiar with the equation for u. So we have two derivatives in r of u plus potential times u is equal to E times u. And we can use our one-dimensional techniques on this equation. And so the next thing we're going to do is to look at a particle that is forced to live in a sphere of radius r. So here is a sphere centered r equals 0. Particle is forced to live inside there. And so we know that the u function, so at r equals 0, u is 0 times the wave function, so that has to be 0. And at r equals big R, or let's say, let's say between, so for little r greater than between 0 and big R, the potential is equal to 0. The particle is free to live inside there, and otherwise it becomes infinite. The particle cannot exit that region. So we're familiar with this. We know how to get the energy levels. So let's at least do that. So at least do that part, this is nothing more than, we had this equation, so inside the well, V goes to 0. All right, so now we are considering this region here, and so the Schrodinger equation looks like that. We're familiar with that equation. Right, that's just the particle in the one-dimensional prison, and so we have the same energy levels. En, and we can just read them off. But we're going to replace that, what we had as L before, with R. And so the energy levels look like this. And the mathematics is exactly the same, but it's for the U function. So we know what these functions are like. We know what the energy levels are. And we just have to go from U to the wave functions, which are really discrete functions as they were in the one-dimensional case.